About to begin our workshop shortly, so we kindly ask everyone to start settling in. If there are any empty seats in the front rows, please feel free to move forward and fill them in. Your participation and presence really help create an engaging and energetic environment. So we're counting on your enthusiasm and cooperation throughout the session. Thank you, and we're excited to get started with you in just a moment. The title of this morning session is What Science is Telling Us About Climate Change. Dr. Gary, allow me to kindly pass the floor over to you.
Thank you very much. It's a pleasure. Good morning, everyone. Pleasure and an honor to be here. I'm very humbled that so many of you are here at this hour of the day 3 already. I get a bit nervous when I'm asked to talk about science of climate change. I've only done it once before. And the idea really is that sometimes science can be pretty dry. So I'm glad this slot is not right after lunch. But just out of curiosity, how many have attended any of my talks before? One, just a handful, okay. How many of you attended the one on climate science last year? You got one, okay, all right. So there are some slides, just for your information, there are some slides that overlap, but I've updated a lot of stuff. And it's not on the same topic exactly either. But welcome once again, and very glad you're here. I guess the idea also is that this is not supposed to be a lecture. So do stop me at any point in time for any reason, and we'll make this more interactive. It'll help keep us all awake. I hadn't planned to keep you here the full 2 hours, but once again, it's going to depend on how many questions you have and how we can get this discussion going, all right? To me, it makes a lot more sense if we are exchanging ideas and making sure that we're all sort of on the front together as we move, and not leaving anyone behind and getting lost, okay? So, I titled this What Science is Telling Us About Climate Change because I couldn't think of a better title. The science, as you know, is imperfect, all right? It's based on evidence. But because the evidence, because new evidence keeps getting introduced, all right, and sometimes even old evidence gets reassessed and re-examined, right? Maybe we have new technologies, maybe we have new ways of analyzing, and there's an example of that in this. Then you have to shift what would be the state of the art of knowledge on that particular topic, and you have to adjust. All right. So no scientist is ever going to defend their opinions or views to the end. And I think it was JD who said, everyone has the right to their opinion, but you don't have the right to your own facts. The facts are facts, right? So I chose these pictures for the title slide because it is interesting that we've had a volcanic eruption that put a lot of moisture into the stratosphere and increased the stratospheric moisture content by 10%. So we're actually beginning to see some of these interesting phenomena, icing on wings at very high altitudes. So what are we going to do today? A little bit about the science of attribution. Not so much how the calculation of attributed emissions, because that's a mechanical thing. That's when you do your reports, all right? And as a bank or an insurance company, you have attributed emissions. That's a physical calculation. I'm going to talk about the science of attribution for climate change. And then the idea that somehow, as we go through our lives, that there is a response to extreme events, particularly those that have high mortality rates, all right? And we make changes after that. And we always assume that post these milestone events will actually have a lower mortality rate. We assume that our adaptation measures, the actions we take, are actually effective. Well, some people have gone out there and they've produced an article that came out in Nature, and that calls that into question, and it asks why. Because I think if you still were to think about it, right, and you think, well, who wouldn't, after a bad event, go and change things to make things better, right? But there are a number of issues there. You know, are you changing the right things? Are you moving the problem elsewhere? Or is the change you're making ineffectual? Okay, and up till now, a lot of people haven't measured that. All right, and part of the issue is that oftentimes we don't handle this issue of vulnerability very well. We pay lip service, sometimes after the fact. All right, they say, oh, these people are vulnerable, so we'll take care of them, and we'll do all the disaster risk reduction, we'll do the early warning and all these things. But next time it happens, you find the same people in the same situation. All right, so that's why we're calling it unnatural disasters, because they're natural hazards, but there's no such thing as unnatural disasters. Yeah, natural disaster, because a disaster happens when you don't handle the hazard. Okay. And then an idea about different kinds of adaptation. There's, reactionary kinds of adaptation that sort of put a Band-Aid on things versus actually doing something that's more transformative, all right? And then I will have some stories from the past that kind of introduce some of these ideas and try to put them into real life, so you can get a sense of how these things actually work out in reality. Okay, so that's pretty much how we're going to go. So if you were thinking that this is going to be heavy into the economics and the calculation of attribution, risk, and all that, and I apologize. This actually is going to be talking about the sort of high-level science. All right. Let's take a look back on where we are. On paper, we've gone past 1.1. 2023, we were 1.48 degrees centigrade warmer. If you look at the calendar year, if you drop January of 2023 and you pick up, if you drop you drop January of 2023, you pick up January of 2024, then we have the first time that we have the 12 consecutive months where it's over 1.5 degrees, all right? And then when we get to 2024, a little bit about 2023 itself, we're wondering why 2023 was exceptionally warm, and we had some of these ideas. We had a very strong El Nino. In 2023, we had this very strange volcano that we'll talk about. We had bad things happening for good reasons. Okay? Yes, bad things happening for good reasons, because we are cleaning up the sulfur in our shipping fuel. So there's fewer sulfur aerosols going up over the oceans. All right? So less sunlight is being reflected off, and we're getting warmer. All right? Worthwhile to have, yes, right? Despite the fact that it's something that's creating and then the other thing is we also had less dust in the air from the Sahara Desert, right? So more of the sun was hitting the seas and made 2023 hot. Now, 2024, no question, okay, 0.72 degrees warmer than this average, and we are actually 1.6 degrees warmer than pre-industrial, and this is the calendar year, right? So 2 calendar years in a row, we'll keep pushing the temperatures up. Now, I'll show you a graph in a minute that might explain why it might not stay here, okay? Because temperatures do this, and that's part of understanding how climate works. But in the end, when we're talking about 30-year time spans, we're talking about average conditions anyway. All right? So Yeah, it's the first calendar year then. All right? All right. When we're talking about this 1.5 degrees above pre-industrial levels, what are we talking about? Where are we measuring? See, because the word atmosphere, if you don't understand the word atmosphere, then it's a lot of this is atmosphere. I mean, so you've got the troposphere, the tropopause, the stratosphere, and all that. Okay, but when we talk about the impact of greenhouse gases, where do they have their greatest effect? Actually, just the surface, 0 to 2 meters, about a human height. Okay? Because this is where we're emitting the greenhouse gases, right? They're all, carbon dioxide tends to be heavy, hangs around, right? So the sun comes in, hits the ground, warms the ground up, it turns into infrared radiation, and the moment it's radiated by the ground, it's already caught by the air. Okay? So most of it is actually trapped in the first 2 meters. And then after that, it's re-radiated and intercepted and re-radiated and re-intercepted and slowly makes its way up with warmer air, etc. But when we talk about 1.5 degrees, we're actually measuring both of these. So up to the tropopause, about 10 kilometers. And that's a long way. It's a really long way. Okay? But this is in line with where all of our weather systems really are, because weather systems don't extend much above this. So this is the part that's warming, because this next part is actually cooling. Okay, and that sounds really strange. We've got 10 kilometers of atmosphere here in the troposphere. It's warming. We've got 40 kilometers up there, and it's not just 40 kilometers in parallel rows, you know, it's 40 kilometers in spheres, which means the volume is actually increasing, right? So the volume is getting bigger and bigger as you go further away from the Earth, right? But the other thing is that you are losing your density of air very, very fast as well. Once you get past 10, most of the atmosphere is below you. When you start getting up to 20 and 30, you're in very, very sparse air. So even though you have greenhouse gases there, the net effect of greenhouse gases up here is that they actually radiate heat to space better. Okay, because there's nothing there to intercept it. So they receive heat energy from down here, they hold on to it, but when they re-radiate it up or down. If they re-radiate it up, they are going from rarefied to even more rarefied, and that heat gets out to space. So the actual effect is that there's stratospheric cooling with greenhouse gases, but there's tropospheric warming with greenhouse gases. Okay? And this puzzled me forever and ever and ever. I thought that from here, you know, you had 1 photon of infrared and it could radiate straight back out to space if there weren't any greenhouse gases in the way. All right? But that's not the way it works. It has to go from here to here, here to here, and so on out. But the strange thing is that we have warming down here, but right above we have cooling. And part of the reason why we have cooling is because it's trapped here. It cannot get there. Right? If we had fewer greenhouse gases down here in the troposphere, we'd have more stuff leaking over into the stratosphere. The other reason is that normally the stratosphere would also be warmed by the presence of ozone, because we've got sunlight coming in and hitting the ozone, and all of that UV, the ozone is blocking the UV, so the ozone is getting destroyed and created by the sunlight, right? But it's also warming the stratosphere. When we have ozone depletion like we have now, we're not out of the woods yet. We've solved the problem of the ozone holes, but we still have thinning ozone, right? So actually more UV is getting in. But that UV is also not being converted to heat, and that's also part of what's cooling the stratosphere. So stratospheric cooling is both caused by the greenhouse gases radiating heat out to space and the lack of ozone, which is not turning UV into heat, right? So both of these are dangerous.
So if the ozone layer is still thin and more UV is coming through, as a UV photon is more powerful than a infrared one,
Yep.
Is that in of itself adding more heat?
Yes, it is. Yes, it is. So the question was, if there is still ozone depletion going on in the stratosphere, and there's less ozone than there should be up there, does that mean that more UV is getting through and actually increasing the warming down here? And the answer is yes. So do keep your sunscreen on and do try to stay out of the sun, at midday. All right. If you can go out early in the morning or in the evening when the sunlight has to come through a lot of atmosphere at a low angle of incidence, you might, high or low, I forget which one is high angle of incidence, which one is low, but has to come in at a shallow angle, you're much better off. All right? Okay. And these things also kind of give us a structure of what we're going to be talking about later on with respect to some of the volcanic eruptions and things like that. Okay. Any questions on this? So you see, you're flying up here as your typical airliner, all right? But this is that scale is in kilometers. Okay, and the stratosphere goes all the way up to 50 kilometers. But like I said, you see where your density and your pressure are almost zero. Okay. I like pictures like this because they give us a sense of what the atmosphere really looks like. Okay, because when we have all these colored bands and we label them as we do on the right, sometimes the scale is very much off, particularly with drawings and diagrams. The scale is very much off. But this gives you the actual scale. Okay, so the units for all of the curves are down here if you're interested, and you will have the slides. All right, this is how it looks. In the diagrams, of course, it's very much expanded for you to see. The troposphere is very thick. You'll have the Earth this size, and then you have all the layers going up, actually going thousands and thousands and thousands of kilometers, but it's actually very thin. What's the you think of the scale? This is from Penang to Seremban. Okay, so this is it. The coat of paint on the basketball. Right, very thin. And that's why as much as we thought that we couldn't change it, we are actually changing it more than we thought possible, right? If you are a bit of an airline buff and you use an app called Flight Radar 24, you will be shocked at how many planes there are in the sky at any point in time. Okay, so we really need SAF, just so you know. Okay, all right. Also, just once again to kind of give you a sense of the direction that we are moving in, and the speed at which we're moving in that direction. So it's very important. So we are of course we are releasing greenhouse gases, right? But the question is, are we releasing them at a uniform rate? Are we releasing them at a decreasing rate? Are we releasing them at an increasing rate? All right, and then thereafter, given the fact that we are releasing them at that rate, what kind of impact are they having on the atmosphere at this point in time? All right, so there's this very nice slider by the European Space Agency and Copernicus, and in the website you can just put your mouse on this slider and slide it along 1990, 2000, 2010, etc. and it will move this 30-year window, all right? The purpose of this 30-year window is basically to calculate this slope, okay? And see what happens as I move this. Now, there are a couple of things to watch. One is the date at which we pass 1.5 degrees, right? So we're extending this line based on this slope. We're extending this line out, and we're seeing where we hit 1.5 degrees and what date it is, all right? So if we take this interval, 1970 to 2000, we can see that we hit 1.5 degrees in 2045, May of 2045. We move to 1985, it gets closer, March 2045. It was May, now it's March. Next 30 years is July 2036. Move it again, February 2035. All right? When we get to here, March 2024, we see that it's come from here all the way back to July 2033. Because as we've gone along, the slope has actually been getting steeper and steeper and pulling that number in. Okay? So if this doesn't convince you that we need to do something very, very serious to change the direction in which we're headed, okay, I'm not sure what will. All right? Now, the other thing to look at is you know, we've got the line, which is the average behavior of this curve right now at 1.27 degrees above pre-industrial levels. But the actual data point is up here at 1.6 for 2024, which is why I said, will we stay there? We don't know. Okay? So if this line were correct, we would need to come down to average, you know, to keeping this line average. But if this line is no longer the average, and we're going to be oscillating between here and here, then this line is going to have to do that. Yeah? Okay. So, I think enough bad news. The idea really is that hopefully this also gives you a sense of, you know, sometimes when you get sound bites thrown out, part of what I'm going to be talking about is how we think about science and climate change through the media as well. Because number one, we have short attention spans. Number two, the media are, for the most part in the world, businesses. We still have government media, you know, and their job can be quite boring actually. Just, you know, sort of follow the ministers around and report on what they do and get sound bites from there. But the rest of the media actually, rest of the world, the media actually relies on eyeballs and advertising and selling newspapers. All right. So I think one example that I had was when we were in Copenhagen during the big blow up, when the negotiations crashed. I still remember they were all the heads of countries were heads of state were in a room together. Small number of them, not all, very small number, and we were just out waiting because they were supposed to sort it out. And Obama was the first to come out, and he went straight to the U.S. press briefing room, and he was followed by a horde of reporters. And all of us ran to the monitors to watch. And he just got in front of the mic and he said, "We have a deal." And all the reporters wrote that down. And then he left and flew away. And all of us went back to the plenary hall because in our minds we were saying, no, we don't. We have to adopt the decision. All the countries have to adopt the decision in the plenary hall before we have a deal. You know? So I was wondering, you know, all those reports went off to file their stories. I said, what are you going to write? They don't understand the process at all. Okay, so it's very interesting. But our news nowadays is so thoroughly curated, that people far away from you on the other side of the world with different cultural backgrounds, different educational backgrounds, different social values are deciding what you want to hear and what you don't want to hear. Okay? So this is where some of the ideas of democratizing information really come in. The reason I put this weather versus climate thing out there, usually when I'm talking to people about this, is because people confuse climate and weather. Who is still confused about climate and weather? Seriously?
No. Very confusing.
Okay, it's actually very simple. Weather is what you get, right? That's weather, right? By 3 p.m., it can be very different, right? If you if you want to put money on the weather forecast for Kuala Lumpur, just have the icon that says sun and then rain, right? Because it's one or the other, and between those two you have 100%. Okay, but that's basically what you get. Now, climate is what you expect to get. It's what you expect to get. Okay, so you come to me and say, I'm going to make a trip. What clothes should I wear? First I say, where are you going? Oh, I'm going to the COP in Baku. All right, so now I know where you're going. And it says, okay, when is the COP in Baku? And you tell me when it is. Then I know what to expect, and I know what clothes to pack. All right? But can I still know the weather there when I arrive? Probably not. Okay, it might be sunny and I could get by with a jumper, or it might be cold and windy and I might need a coat. All right, but the linkage is that this is obtained by averaging this over long periods of time and understanding how this behavior works, given the seasons, etc. Right? So when we're doing climate attribution, then things become a bit strange, because if I have an extreme weather event, all right, and I want to say, did this event, which is a climatic event, did this event, which is a weather event, an extreme weather event, okay, how much of it was due to this? Then it's like I'm mixing apples and oranges. And that's why the attribution is such a difficult thing to understand. All right? And that's kind of why we actually have a science of attribution, which is at the same time an old science and a very, very young science. Because many times for these sciences, it really takes a long time to tease out all of the difficulties. Okay? What you get and what you expect. Now, the part of the reason is that these extreme weather events, they have multiple causes. Okay? They may be impacted by topography, they may be impacted by geography, the seasonalities, all of these things, and then on top of that, greenhouse gas presence, etc. Right? Butterfly effect in the end, if you need to. All right? So the science of detecting whether man-made global warming was one of those causes is the science of attribution. So how much of what happened there can you attribute to man-made global warming? Right. And once again, it can be very coarse, right? Many times, if we have an event, we might be able to say if it was more severe or less severe because of climate change, but we can't say with certainty whether a particular event was caused by the presence of greenhouse gases. Because, like I said, if there are multiple causes, which cause became the trigger? It's really not possible to say. Okay? So, So in a yes or no sort of way, it's going to be practically impossible, all right? So we can talk about attribution of a phenomenon. That's the biggest scale, okay? So let's talk about the attribution of this phenomenon of elevated temperatures, right? So how much of this increase in temperature is due to climate change? So this is at the coarsest level, so it's actually the easiest to tease out, right? You take all of your natural drivers of climate, natural forcings, okay, natural methane from swamps, from wetlands, okay, and put all of those in the model, and you get one curve. And then you put in all of the anthropogenic or human sources of greenhouse gases, so the rice from, the methane from the rice that we grow, the methane from the poultry farms and the poultry waste, the burning of fossil fuels, etc., and we get a different curve. So in terms of a phenomenon, then we can have an attribution, right? So this curve is attributed to greenhouse gases, elevated greenhouse gases in the atmosphere, and this curve is without, right? So our confidence is fairly high on something like this because it's at the broad scale. If you were to talk about individual events that are suddenly extreme, okay, so we have all this rainfall information, all right, over the years, and we've got how many stations we want to know, okay, recorded extreme rainfall. And here we use what statisticians tend to use all the time, standard deviations, all right? So how many standard deviations are you away? So you say, okay, if you're more than a certain number of standard deviations away, then we can say you are an extreme event, right? And if you have an extreme event, then you might be able to, based on the time that that extreme event occurred, the conditions under which that extreme event occurred, see if there's an association that you can then use for attribution, right? Now, this is actually harder than the next one, because this is just an individual event with an individual magnitude, okay? If I were to run a model, all right, most times the model would not come up with these things, okay, because there are rarities, there are unexpected things. Most of us, when we create models, we try to create models that actually produce things that have a high likelihood of occurring. Right? Models aren't designed to find things with low likelihood of occurring. Okay? The only time you want to look out in the tail of a model is when you actually have an experiment that you've got a control and you've got your treatment, and you want to know if your treatment is sufficiently far out in the tail to be called a difference of effect, to establish a difference, right? But normally you don't start out with something that's out in the tail and say, well, is this part of this or isn't it? And if it isn't, then how do we attribute that? Okay? The next one is a bit easier because it's return period. Now, extreme weather events we know can be higher in intensity, can be more frequent. So the first one was the intensity, and this one is the frequency. So it's quite easy. We've got 5 extreme events occurring over the span of 437 years. All right? And so we've got 0.01 or 1% of all the years. So it's got an average return period of 100 years. Right. Now, this we can track over time. And we can line it up and try and correlate it with greenhouse gas emissions, and we can see if the return period changes over time. Okay, so with this we have a bit more confidence. the other way that we can do it is actually, like I said, we're looking out in this tail, right? And this is the place where strange things happen, and extreme weather events all happen out here in the tail because they are infrequent, right? What we do is we sort of sort everything from lowest to highest, and then we take the highest 1%, the 99th percentile, all right? And then we compare some period 1940 with some simulation 2050, all right? And we look specifically at the tails, and then we compare the area under the tails. The area under the tail, there's a difference. In this case, the area is 5 times larger on the light blue than it is on the dark blue. Then we can say that there is a chance, it's 5 times larger that we will encounter events of that magnitude, okay, in 2050. Now, I've left the model here as a bit of a black box, okay? But these are models that climatologists and physicists, mathematicians use all the time to generate these distributions. And they've been used for many, many years, and there's a fair degree of confidence on their accuracy. Okay, so it would be models like this that would be used to assess, say, the difference between a 1.5 degree increase and a 2 degree increase. All right, so you feed that into this model, and then you look at the difference for various types of events. Okay, and this is once again how frequent or infrequent they would be occurring. All right. Okay. So I said that this is a science, and usually scientists like to get their work published. So we'll see there have actually been more than 170 studies looking at the role of human-induced climate change, and they've been studying about 190 extreme weather events. Okay, and this is the range of weather events, and you can see whether they are more likely to occur in red, okay, less severe or less likely to occur, that's in purple. Okay, no discernible human influence. This is a very important one. You can't find a difference either way, not more, not less. You can't detect it. Okay, it's a valid finding, right? And then insufficient data or inconclusive, also another valid finding, right? But this gives you a sense of, you know, where some of these things fall in terms of the kind of hazards that you might face as a consequence of these extreme weather events, right? So heat is pretty much, like I said, it's the phenomenon at the phenomenon level, right? And that's why we have lots and lots of studies, lots and lots of data, and we have, in fact, very, very strong confidence. Because if you look at no discernible human influence and insufficient data, it's actually a very small part of it. Okay, for droughts, it's a bit more iffy, because, you know, droughts can be less rain for a long time, or it can be no rain for a slightly shorter time. There's many ways to have a drought. Okay, there's only so many ways to be hot. Okay, but there's many, many ways to have a drought. All right, you can have no rain when you're supposed to have rain. Okay, when you hit the monsoon, you're supposed to get rain, you don't. Okay, or the rain comes from a different direction, and so there's a mountain range in the way, and you don't get rain. Okay, from that particular direction. All right, Malaysia is interesting, especially peninsular Malaysia, and the monsoons for us is always a lesson, because, you know, we here on the West Coast, we are supposed to get our rains in the summer, right? And then the East Coast is supposed to get their rains in, quote unquote, the winter. But our mountain range is exactly perpendicular to those two monsoons, right? The issue is when things get messed up with the El Nino and with the Indian Ocean Southern Oscillation, we get wind coming up parallel to the peninsula and parallel to the main range, Titiwangsa. Okay, and that brings rain up from the south, but some of it goes on the west coast, some of it goes on the east coast, and it's very confusing. Okay, so the intermonsoonal period for us, number one, its timing has gotten weird. Okay, we'll have monsoon, then we'll have no monsoon, monsoon. And then the other thing is the effect has gotten weird because of the wind direction, to the point that our durian trees are so confused and they don't know when to flower and fruit. And that makes, that makes us humans confused because we time our life by durian. At least we in Malaysia do. Okay, so and there's some that it's almost too difficult to say one way or another, because localized cooling can occur because of warming, and that's because the circumpolar jet stream can weaken and spill cold air out. Okay, which was for a long time used by the deniers to say, what global warming? It's the worst winter we've had. We've had more snow with lower temperatures, but it's all, if you look back at the science, it's because of the phenomenon that weakened the containment of Arctic air up there in the North Pole. All right, so these were collated by nature. Nature is of course very reputable and carbon brief. Heat includes the heat waves and wildfires. Very, very strong linkage there. Not so much for us, but for areas where the forests are a bit drier, savannas and the like. They really become tinder boxes when it gets extremely hot. For us, the issue is actually more of human safety and behavior because of our humidity. In many parts of the world that burn, the air is actually drier than it is here, and so the humans there are safer because when they perspire, the perspiration evaporates and cools them down. Okay, but you'll hear Datin Sunita talk about wet bulb temperature. That's what most of us in Malaysia feel like. Our clothes are stuck to our bodies because the humidity is so high, we cannot lose heat by perspiring, and that's the issue. So I took the train here, so I walked from Bandaraya across, and yeah, you do get a good workout and a bit moist. Okay, so oceans, yeah, you shine, ladies, you shine, yeah, shine. Yeah. So the marine, of course, includes coral bleaching, and that's why oceans does have a strong confidence in their response. Okay, but some of the others slightly weaker. Okay. All right. And then this once again kind of ties everything up. We've got ability to detect the possible influence, and depends a lot on how well we understand all of these influences. All right. So once again, we have extreme heat and extreme cold up here, and then we have the droughts kind of in the middle, and then some of these convective thunderstorms. These would be what I talk about KL weather. When you look at that, if you want to bet on the sunshine and rain icon. Okay, because these are what these convective thunderstorms are. Right. Any questions on this idea of how we try to attribute, and how we begin by attributing phenomena and then move to more like things like return periods, and then have the least amount of confidence on things like individual events, so that and then at the really far end, the intensity of any extreme weather event. All right? Yeah. Okay. Oh, yeah, sure.
Oh, no. I think not enough, right? Thanks.
Yeah, it's for the recording.
Oh, for the recording. Okay. I think when we see this, right, and we see the heat-related events are mostly strongly related to human influence. I think it kind of signals us where we need to focus the adaptation. So it's more on urban cooling. So we see like heat and drought are pretty much highly influenced by human activities. So I think it kind of gives us priority on the climate adaptation plan in a way.
Okay, I need to put a cautionary note on that, because these are not events, they are studies of events. Okay, but you're right in saying that the linkage is very, very strong, right? So regardless of how many studies there were on what, and indeed the same data was probably used for more than one study, right? If people were testing different hypotheses, they were testing different ideas, different relationships, okay, functions that they use to model these things. But once again, so this is a compilation of studies. But you're very right in saying that for us, particularly outdoor activities and the like, particularly also with the fact that we talked about the fact that the ozone is still thin, okay, and the UV is getting through, we do need to think very much about how and when we do outdoor activities. So in the 80s, when I was in high school, my dad left to work in Saudi Arabia. He worked in shipping, so he worked in Jeddah, Jubail, Dammam, and Riyadh. And there, they load and unload ships at night. Yeah, they just flood the whole place with light and do it at night, all right? And what I've realized recently is that in downtown KL, we are building buildings at night now. We're beginning to do that because it's safer, you know. And there are actually some safety benefits given the fact that there's fewer people around. You know, there are also fringe benefits ideas. But the idea really is that I think that's a strong adaptation move, a sensible one. All right, and I remember a long time ago I read a short story about a sighted man living in a valley of blind people, and he stumbled on this valley and he lived among these people, and these people slept during the day and worked at night because they were blind. And he eventually, a nice ending to a short story, eventually he blinded himself so that he could live with them. Interesting philosophical idea. But once again, you know, the idea is, why don't we question some of these things more when we think about how we do things? Yes, Fiona.
I'm just curious, how might some of our biases play into these attributions and determining these attributions?
Definitely, but that's the first thing that the scientific community is trained to do, to actually look to all the possible bias-reducing methodologies and tools. You go into any study knowing there's going to be bias, and you do control for that. More so when you're dealing with things like surveys, but when you're dealing with data collected from instruments, then it's much less of a problem. That's why you will hear Sunita saying wet bulb temperature as opposed to asking how many people, you know, wore too uncomfortable clothes today or something like that. Okay, so surveys and all these things, very, very open to bias. I think the idea really is that as a science we are mature enough to understand some of these things and sort of nip them in the bud right at the start. So and scientists, oh, believe me, they are the first to point out during the peer review process, you mess up on something like bias, and, you know, you'll never get that paper published. They'll all jump down your throat and get you to fix it. Yeah, yeah. If you know, and once again, there are allegations that the scientific community, like any other career orientation, you know, does need continuous funding to survive, etc. And there be allegations that they over-dramatize things, you know, to make sure that there's continued funding and things like that. But I believe that you know, the scientific process actually does keep them honest. Okay, and if any profession, reputationally, scientists live and die by reputation. I think it was Harvard School recently. They've had some behavioral scientists, you know, alleged to have fabricated data, and very high profile, very glamorous scientists, and out. Bye-bye. Bye-bye. Very, what's what? A lot of, yeah. No, yes, go ahead, please. That's fine. No, that's fine. Charismatic, very charismatic people, okay? But once you are proven to be fabricating data, you're out, yeah.
I think that's different. Thanks, Dr. Gary. You know, you talk about, referring back to your previous slide, right? There is a correlation, but there's no causation.
Causation. Oh, yeah, the one is very fun. Yeah.
So then it comes back to that piece of research. When you talk about drought, rain, especially when you talk about there's the part or the study that say there's no discernible human influence. Mm-hmm. So when it comes to drought and rain, that's an event, but can it be actually indirectly, there was actually human induced that changed the precipitation patterns, which then leads to flooding? It's not a causation, but is it correlations? Like how do you actually interpret this?
Yeah, I mean, inconclusive just means inconclusive. You can't say whether it is associated with, or you know, whether it can be attributed or whether it cannot be attributed. And all data has this kind of noise. Yes. All right. It's just in some cases it has less noise, so it's easy to pull out whether it is attributable or not. In some cases it has more noise, right? No, yeah. In this, you can't use this to deny climate change, and you can't use this to add to this either, because you have to keep the scientists honest.
Yes, I understand.
And hold their feet to the fire.
No, I'm actually particularly interested in the blue one. Mm-hmm. Inconclusive data, that's fine. It's just the blue parts that actually in the drought, the rain, flooding, that two events.
Well, like I said, you know, there are many ways to have a drought, and there are many studies involved here. See, so there are maybe 12. It's like 30 to 40. Yeah. So it's maybe 12 studies there, right? Maybe eight studies there. Right. So number one, the number of studies in all of these falling into these categories is different, but we don't know, you know, what kind of conditions they were dealing with. Okay. Right? Like I said, there's many ways to have a drought. Yeah. You can have no rain when you expect rain. You can have less rain over a long period of time. You can have no rain but for a shorter duration. You know, so these kinds of things. Now, look at the 3 consecutive years of La Nina that we had before we came back into this 2023 El Nino cycle. Yeah. Right? We had La Nina for 3 consecutive years, right? And each year, the moisture balance in some of the most productive prairie areas of South America, so we're talking Argentina, Brazil, all that, yeah? They just had less and less and less water over those 3 consecutive years. And in the end, the last year, the soybean crop in the spring, they planted it, but there was so little rain that they just didn't even bother to harvest. I mean, the fields were in such bad shape, the plants were so small, you know, most of them were dead, some flowered but never set fruit, never set pods, right? That filling up the harvesting, filling up the harvesting machinery with fuel to go in and harvest that is not feasible. Not feasible. So they just left it. You know, but can you say attributable to a La Nina? And then can you say 3 consecutive years of La Nina, how often does that happen? And then can you say that that's attributable to changing climate patterns? Okay, so in some cases it has to be something that you work backwards until you get to the climate. All right, but in that case, to me, it's very, very clear. In my mind, at least, when you have El Nino, what the impacts are. When you have La Nina, what the impacts are. And you could just model that same La Nina continuing for 3 years, 4 years, 5 years, 6 years, and sure enough, you will just get drier and drier and drier. Okay. Yes, Dato.
I could ask you personally, but I thought others might be interested to hear from you. So 2 small questions and 1 comment. The first, after major events, there are a lot of people coming up very quickly to attribute, right? To make claims on attribution. Is there one place that where people should source? I mean, is there one reliable place you think people should go to see more truthful attribution claim?
Not individually by event within the first year of the event. It's just not possible. I can't, I can collect data from the event, but then I have to collect, a whole suite of other data around it, and then I have to analyze it in the context of the ambient conditions at that time to see if that works. So many times what happens is studies like this, or individual studies that go into this. Okay, I will look once again at things like return period. I will look at intensity. I will look at localized conditions. All right, and that's the only way I'm going to gain a sense of. It also has to do with very, very, very local conditions, which may be impacted by systems, local systems, like, for example, the Indian Ocean Dipole, interaction of the Indian Ocean Dipole with the ENSO, the El Nino system, all right? And then there's even a third system that kind of worms its way around the equator, all right, and comes around periodically. So just like the tilt of the axis, the wobble of the Earth, all of these systems, sometimes they reinforce each other, sometimes they cancel each other out, right? So the Indian Ocean Dipole and the El Nino, sometimes they combine to make things worse, sometimes they cancel each other out and help the situation.
And second question. So is there a repository of all these studies in one place, or we have to go all over the place to look for these studies?
Attend your class every year.
No. I mean, I don't know. UNFCCC
No, actually, if you ask DeepSeek or if you ask ChatGPT, they will already be able to pull all the links out for you. In fact,
they'll create a story for you.
You ask them the question, they will answer the question. Now, I didn't do this using ChatGPT. I actually looked for, but I think I've said it before. I've used, when DeepSeek first came out, I just asked DeepSeek, what are all the scientific disciplines associated with climate change? And then what are associated scientific disciplines that, that are needed to understand those disciplines to understand climate change? And then I said, if I were to design a course that would enable me to understand this, then what should I read? And then, it's really helpful. So use AI wisely, and it will really, really, really help you. But be careful if you're a corporate, and don't use the public versions, okay? If you deal with individual data, don't, buy your own version, train it in your own company, and use it within your own firewall. So.
And the last comment, I think, fine. I take the AI thing. So it's very difficult unless you use AI to find all these things. Yeah. Last comment on the adaptation part at night. I just want to mention that on the work that I do, you know, for example, some people are harvesting at night from agriculture sector, and that there is some indication that it affects your integrated pest management negatively.
Yeah.
So beware of maladaptation. It might be a good idea, turns out to be a bad idea.
But yeah.
Thanks.
Yeah. So yes. So you know, if you are hand harvesting, and you have nocturnal reptiles like snakes, etc., you know, you have to be careful. So as always, it's an issue of adaptation and co-adaptation, evolution, co-evolution, etc. Right? But yeah, you have to worry about these things. In fact, our light pollution is something that really we should be managing. If you go to Bangkok, you'll find that I think after 2 a.m. or something like that, the insects finally find peace. Yeah, but here, not only is there light pollution, I've actually calculated how much electricity it takes to run those billboards. And even just, you know, 20 meter by 20 meter billboard uses as much electricity as several big houses. Yeah, and so, you know, but it could be a win-win situation because, you know, before you shut the billboard off or before you put it on low light level, or even when you put it on low light level, you can put your ad up there that this company owns this billboard, is going green by shutting this billboard down, and you can have it there. And so it can still function as a billboard, it can still look after your reputation, it can still also signal your conscientiousness in terms of green practices and lowering energy consumption, etc. All right, but it can once again be bio-friendly at the same time. Yeah, they solved that problem recently about the insects flying around the light. Okay, the insects are just trying to fly in a straight line, and they're just keeping the light on the same side of them. Okay, so when the light is the moon, there's no problem. I'll fly in a straight line because the moon is far away. But the moment the light source is very near and I keep the light on my right, I'll end up going in a tighter and tighter circle. So very recent science, but very interesting. Anyway, all right. So now this last one is kind of an interesting one because this particular study looked at events around the world, all kinds of events. It's a bit small, hard to see. Convective storms, tropical cyclones, floods, glacial lake outbursts, drought, heat waves, and fire. And they actually looked at whether there was no known attribution, okay, role of climate change likely, and then attributed to climate change. Okay, so once again, so this is kind of where the chips fell in terms of what people decided. Okay, for 2 consecutive years. So once again, you can see that there are some cyclones that are strongly attributed to climate change, and there are many storms that you can't really attribute. All right, and if the number of storms keeps increasing every year, how do you know which ones are the quote-unquote new ones that were generated by climate change? See, because it's all smeared across probabilities. Yeah? Okay. All right. Okay, before I go to this slide, I'd like to ask if there are any questions and do a bit of a time check. It's been an hour. Yes, sir.
Hi, Gary. My name is Bert. I'm actually trying to finish off my master's in sustainable development. I've got a question here to seek your views. All right. Looking at the science, it's fairly consequential measurements that you're seeing right now. From start of the century, 1900s, there's only about 1.6, 1.7 billion people. Today we're sitting at probably 8.5, 8.6 billion.
Billion, yeah.
Right. What's your view? right? How much of this can we do? Because what you're seeing right there, it's all the highly populated areas that you're seeing the consequential effects.
No, I think we were you at yesterday's session where we were actually talking about, and Joe De Cruz was actually talking about population and food supply.
I know, but I
Okay,
I
yeah. I know. I basically share his views. You know, for humans to have a dignified existence and not be killing each other, okay, we do need energy and we need food. And once again, if you are at a population size where the number of Earths we have can provide us with that, you know, in a pretty much sustainable manner, then we can say that we're on fairly safe ground. But once again, if we look at the projections and we see that population is going to increase, look at where it's going to increase, then we need to be thinking very, very carefully about how to manage this so that we don't end up with great amounts of inequity, all right, a lot of conflict, and a lot of human misery and suffering. Okay, to me, that's what it boils down to. Okay, and the nuclear argument that we were talking about yesterday, right at the end, is enticing, because when you have the kind of energy density that you have with nuclear, you can turn anything into hydrogen. Okay, you just expose it to those very, very high temperatures, it will disintegrate and you'll get your hydrogen. Okay, I don't care if it's methane, I don't care if it's coal, I don't care if it's biochar, whatever it is, your trash. Okay, at very, very high temperatures, you can separate the hydrogen off and you can use the hydrogen as the hard to abate fuel for mobility and things like that. Okay, depends if you want to use it as ammonia or whatever it is, right? But the rest is electricity, you know. So as long as you can hook a wire to it, that's fine, or hook a battery to it, that's fine. But it's the stuff that moves around a lot that you know might need. But you know, so it's that's pretty much. I hope that answer. Yeah, right. Yeah. But that jolts my mind about something, and it was not long ago that I read something. It was a paper put out, quote unquote, by working physicists, and the paper by working physicists basically said that we should continue putting more CO2 into the atmosphere because the agriculture needs more CO2 to grow more crops to feed more people. And immediately I completely bristled, and you know, I was like cussing and swearing at the at the screen, because if you're a working physicist, of all people, you should realize and understand that food has never, you know, food production has never been the issue here on the planet. The issue has always been that the food will not grow where the people need it. Okay, that's the issue, because if you walk into any grocery store and look at the entire inventory and look at all the use-by dates, you will realize how much stuff actually gets close to the use-by date and they take it off the shelf and do something else with it. All right? In the US, that's 30%. That means 1 out of every 3 cans of a particular product, you know, doesn't get consumed, and yeah. So production has never been the problem. How we produce and all that, we can argue about that. You know, whether we use too much fuel, too much water, we overproduce, you know, to make our lives easy. But that has never been the issue. Okay, but thanks for the question. Tough question. Okay. All right. Any other questions on this before I go to the next one? Because the next one is kind of interesting. It's about before and after. Okay? you have a landmark event that results in a lot of fatalities, right? You make changes to your policy or your infrastructure or your governance, whatever it is. Do you see an effect coming from that? All right, this is the line. You'll see there are developed and developing countries on both sides. On this side, there's a significant mortality rate pre and post. Okay, so it should be higher pre, it should be lower post, and it should place you on the graph that way, right? But you still see a lot of countries, both developed and developing, where they can't, either they can't bend the graph, or the graph gets worse, you know, despite the fact that you had a landmark event that would have, you should have triggered, and probably did trigger, okay, responses, okay? So you can see, I mean, you'll have this slide so you can actually look at which countries are where and how they're distributed up there. But to look at all of them, okay, you see Haiti keeping the, so Haiti is, you know, really one of the most destitute countries, and they're managing to, and they get hit by cyclones, yeah, the Caribbean, all right. You see some countries that, you know, seem very, very good early on, but then they can't fix it. But Indonesia, able to pull it down. Ethiopia, Algeria, okay, Peru, all right? And then on the other hand, you have Sri Lanka, difficult. Thailand, some improvement coming down, okay? Some obviously not so good. Pakistan, with great difficulty. Where is Malaysia? Yeah, they didn't run this study in Malaysia, and I suspect that at the time that they did this, they didn't have the data from the 2021 flood yet, okay? And even in that flood, we didn't have that many fatalities. Yeah, double digit, but you know, when you're talking Pakistan, you're talking like, so, yeah, so chances are we are once again, you know, because of the good fortune of the Creator, you know, spared a lot of these things. So we are seen probably as an outlier. Yeah.
I think it would be interesting to compare to Scandinavian country also.
Yeah, we okay. Yeah, the only one they have up there is France. Okay, and it falls. Where is it? Yeah. So So where's France? Okay. So not all that good. I mean, it was coming down before, and then they you know, leveled it out, but it should have maintained on that trajectory or gotten even worse, gotten even better. That means the number should have dropped, number of fatalities should have dropped. Oh dear, wrong title. Oh, sorry for that. That's from a future slide. Okay, okay, all right. Did I do that? Oh, okay. Okay. So the idea really was that what I wanted you to think about was this idea that often doesn't get enough attention, and that is this idea of decreasing vulnerability. Exposure, oftentimes you can't really, you know, either you're exposed or you're not. But a lot of times we see we treat vulnerability as something that we always deal with kind of after the fact, right? And it's something that we somehow can't seem to wrap our heads around. So I was attracted to this. There's no such thing as a natural disaster, only a natural hazard. Okay? So if you have a natural hazard, then you should already be thinking about exposure, you should already be thinking about vulnerability, you should already have implemented adaptations so that you can avoid having the natural or unnatural disaster. Okay? And if you don't think of this, then you will end up there. Of course, the illustration is a volcano, but the idea is pretty much the same. Okay? When you're talking about trying to reduce vulnerability, then we are talking about adaptation. And in this particular study, the author really talks about, for most countries, what happens is kind of reactive adaptation. Right? So in the case of floods, what do? They try to protect the area by building walls or dikes or other kinds of barriers, installing pumps, all these things. But when you think about it, all these things do is displace the flood water from one place to a new place. Because obviously the place where the water came from is already saturated. If the water level is high here, that's why it's coming to where you are and flooding you. And if you put a wall there, all that does is raise the water level on the other side. And then it goes to other places that didn't used to flood before. All right? So we talk about this reactive adaptation and incremental adaptation and say that for most countries, part of the reason why they end up not being able to make that change after that landmark event, that milestone event, is because they are doing this reactive adaptation. All right. So what does transformative adaptation look like? That should be the base of the pyramid that they're talking about. Okay, so to me, rumah tiang has always been transformative. Okay, because the water stays there. You don't move the water. That is really adapting. Houseboats, okay, the water is still there. The water still gets to move there because the water was there before the houseboat came along. The water was there before the rumah tiang came along. It's just an issue of seasonality and when. All right? So when we think about long-term planning, all right, what we really need to think about is transformative adaptation, or actually adaptation that used to work in the past when we had only old tech but very, very effective tech, like rumah tiang, okay, and it actually did work. Now the idea also is that when we move from this kind of adaptation to this, we are actually thinking more of the long term. All right, and if you build this in, you can actually weather more severe climate changes in the future as well. Right? Otherwise, you react to one level, you'll have to react to the next level. You have to react to the next level. Okay, there's no end to this side. Okay. Right. Why does it keep turning off when I forward it? Could be the battery. Or okay, it's the video. Okay, so this video, a short video. Okay, do you want to take a break? No? Okay, continue. Great. All right, just 1 minute video about the Hanga Tonga eruption. Go ahead.
January 15th, Tonga eruption sent tsunami waves and an air pressure shock wave around the world.
The shock wave pushed small tsunamis in front of it, so it generated tsunami in all bodies of water. And even more surprising was that when this shock wave, which moved about 300 meters per second, was over deep water, like a trench, it was pushing water at about the same speed as it was moving. So there was resonance there. It pumped energy into the wave and created a bigger wave. And that's the wave that hit Santa Cruz.
We first got wind of it around midnight on Friday the 14th of January here in Santa Cruz. And then the following week, we were performing surveys of the tsunami damage in Santa Cruz Harbor and surrounding beaches. We just knew that from post-tsunami surveys of other events that this evidence can expire, or it can go away pretty quickly. And our data is very useful for validating models of the tsunami in the far field, which is in the, very far away from the actual source. So this event, the January 15th eruption, is very unique. So the last similar event would have been 1883 Krakatoa in Indonesia. That killed tens of thousands of people, and it was also a large volcanic eruption with a pressure wave that went around the world and a tsunami that went all over the Indian Ocean, maybe even the Pacific too. With our busy lives, we're very much into what happened today, what happened last week, and we forget what happened a long time ago. And the geologic record keeps that. And it's so important for people to know that large tsunamis have happened in an area in the past, and that leads to planning for future tsunamis. And that planning will decrease destruction of property, and it will save lives.
Okay, so how many of you heard the name of the volcano Hanga Tonga, Ha'apai? Yeah. So this volcano, which at the beginning looked like this, all right, the profile is a bit exaggerated because it's only 1,000 meters this way, but if you look at this scale, it's kilometers. Okay, so it's a 5-kilometer wide caldera, and it's just below sea level. Okay, so this is a strange volcano because most volcanoes either it's all on land, then when it erupts, you get CO2, you get sulfur, you get the sulfides, they cool the atmosphere, you have a plume, etc. Right? If it's deep underwater, it kind of bubbles up and you get, But this thing, when the caldera collapsed and seawater went in, it blew up higher in the atmosphere than Pinatubo, okay, 57 kilometers up. So if you were looking at that video, you could see the pointer was at stratosphere. Look, yeah, okay, and I think that the previous record holder Pinatubo was 40 kilometers. This one went to 57 kilometers. And the important thing is that all of this seawater flashed to steam and went up into the stratosphere and increased the stratospheric moisture content by 10%. And you know that water vapor is a very serious greenhouse gas. It keeps us alive down here, but in this particular case, it's strange. Now, that is the size of the cloud, 400 kilometers across, compared with Australia. If this had happened anywhere else in the inhabited part of the world, we would be in trouble. As it was, Santa Cruz is 8,000 kilometers away from this volcano, and the tsunami reached there. The tsunami killed either 3 or 5 people in Peru. But that was, yeah. So these are non-climate related events that can have climate related impacts. And this is one of the reasons why they say that 2023 was hotter than normal, because, so I've covered all of this. So basically all this material, post-eruption, the profile, all this material went up in the atmosphere together with all the water vapor and the steam. Okay, so imagine it's 5 kilometers across. It's a lot of stuff. Okay, and this is how the plume panned out for the year 2022 and 2023. So these are the aerosols, the sulfur. At the end of December, January, then some small traces. And then they started going around the world and coming back, on the other side, disappearing in the south and reappearing in the north. The water vapor at 25 kilometers, remember the first graph I showed you? 25 halfway between 10 and 50, where the stratosphere is. This is measured at 25. Enhanced water, and then persisting all the way through the next year, 2023, all right? And then ozone and temperature anomalies, okay? Either not greater than usual estimation. So remember what I said about cooling the stratosphere, yeah? So moving to the cooler side of the stratosphere. So these anomalies, non-climate related, but with climate related impacts. And these are things you have to look out for moving forward. Another thing we need to look out for are kind of weird tsunamis that actually do have a basis in climate. A lot of the far north and far south have a lot of fjord land. And fjords, you know, exist because we had sea level rise. During the ice ages, the sea level was much, much lower because we're all locked up in ice. The ice was in glaciers. Glaciers, you know, live in U-shaped valleys. Okay, you learned that in Form 4, I think. Okay? So when you have glacial retreat, which is a slow onset process, right? You have a U-shaped structure that was previously filled with ice supporting the bank. But when the glacier retreats, all of a sudden the ice level drops and you've got this big overhang of material. All right? And if it's far inland, maybe the glacier's in the Swiss Alps or something, you're going to get a landslide. But the problem is when you're dealing with fjords, then we get glaciers, you know, we get landslides falling into the fjords and generating enormous tsunamis. We're talking about tsunamis that can swallow a cruise ship. All right? So this happened, and it generated a seismic signal for 9 days, sloshing back and forth across the fjords. And the seismologists had no clue what it was. They could see the signal, but they didn't know this happened. And it's only later on that they went back and found out what it was. Okay? And it's called a seiche when it does that. But you can see the loss of the support and the entire mountainside went. I think it was something like 33 million cubic meters of material that went in. This isn't the first time we've had tsunamis from either landslides close to fjords or actually landslides underwater, right? This is a video of a tsunami that happened in 2017, but this was as a result of an underwater landslide. Okay? So there are men there screaming in Danish. I've spared you the audio. But that basically is run for your life. Okay? No one was hurt at this location, but a number of people whose homes were swept out to sea at another location were killed. Okay? And this is the biggest of them all in Alaska. This is an old photograph. This is where the landslide occurred. Okay? And this is the profile of the hill here. But the highest run-up, basically this was trees all the way to the water's edge. All of this was trees to the water's edge. Okay? But when the tsunami came out, it ripped all of these trees out. And that run-up there is 500 meters. From the water in the fjord to where the trees were removed is 500 meters. Okay? So once again, this is happening in areas that mostly uninhabited or very low levels of habitation, and so the loss of life. But you can begin to think about some slow onset events like sea level rise. Dr. Daryl sitting behind is very fond of saying that when you have sea level rise, you have to recalibrate your entire drainage profile. Okay? And then any kind of events that involve large amounts of energy, energetic water, you have to really think about those things seriously as well. Right? Slopes are becoming less and less stable because once again, if we get increased rainfall, or if we get intermittent dry periods followed by sudden rainfall, all of these things destabilize slopes. And these landslides can occur in dams. If they occur in dam catchments, they can ruin the dam. If the dam goes, then everything below that can go as well. So it's time to begin looking at all of these things and begin measuring them. One hypothesis about the gas leak is actually movement, soil movement, which can put a lot of stress on pipes and can rupture pipes, or can even move pipes away from where you think they were using GPS to a different place where the GPS tells you there are no pipes because you're using GPS. Okay, so I think it really behooves, if you're a business that deals with the kind of infrastructure that somebody else is responsible for, some government agency or something like that, okay, you need to start thinking about, engaging and asking the right questions, okay? If your business lives and dies by pipe gas, if fiber optic cables. Oh, when Hanga Tonga erupted, the underwater landslide took out the fiber optic cables to a bunch of Pacific Island countries. Okay, and that underwater landslide traveled 100 kilometers. The ash cloud was 400 kilometers. Okay, the underwater landslide was 100 kilometers, and that's how it took out the fiber optic cables. So no internet for how long they were cut off, right? So once again, all of these things, if relevant if material to your business, you really should be thinking about them. The last thing I'm going to talk about is once again a slow onset event that has important implications. We normally think of sea level rise as something that happens very slowly. We assume that at least from the time that Homo sapiens came out of Africa between 300 and 400,000 years ago, that Greenland was covered in ice. But we took samples in the 50s. We stored them. In the 50s, we didn't have the kinds of technology to analyze organic material and minerals for the last time they were exposed to the sun. Now, in the intervening period, we have developed techniques to actually date when the last time something was exposed to sunlight, right? And at the bottom of some ice cores, we have found soil cores, and we are now able to date those soil cores from Greenland. And this is the next and final study that I'm going to talk about. Camp Century was established as a Cold War site. They were thinking of how to store missiles in Greenland during the Cold War with Russia. Okay, but look at how far inland it is. Right, that's the first thing. Second thing, this is a bit of the timeline. Around 1961, they were coring it, they brought it up. They were kept in New Hampshire, then they went to Buffalo, and then eventually at the end they were analyzed using some of the latest techniques. So these soil cores are at the bottom of ice cores, right? This is what it looks like. At Camp Century, the ice core was 1,300 meters thick. So not only were they that far inland, okay, they were standing on top of ice that was over 1,000 meters thick. And they drilled down to it, and this is the stuff they found at the bottom. These are indication of whether it was macrofauna, microfauna, macrofossils, whether they were cosmogenic nucleotides that could be used to date these things, what kind of rocks and minerals there were, physical and the chemistry. So they ran all of these things across a whole bunch of locations on Greenland, which is now, covered in ice, except at the edges, right? And they found not only soil, but if you look at this section here, you will see that this upper part is between 500,000 and 1 million years old. So remember I said we, as a species, came out of 300,000. So 300,000 and 500,000, this was just before we emerged as a species. This is much older down here. This is much older. Okay, but even then, it's only about 3 million years. Right? But this is the kind of stuff they found. They found leaves of plants. They found fungal bodies, seeds. These are oospores of water weed and a kind of algae. And then these are insects. Okay? Not only that, they have twigs. Okay? So we've had forests producing these things, standing in what we thought would have been ice for at least 1 million years or more. Right? Now, what's the implication of no ice in those areas and forests in those areas? Well, if you go back to this picture, the implication is that there is no ice on top of those locations. There's not. This is 3,000 meters of ice. Right? If this ice is not here, where is this ice? It's in the oceans. So we're talking between 1.5 and 5 and maybe even up to 20 meters of sea level rise. Right? Okay? So, not to alarm you, but once again to put this in perspective, that graphs and pictures like this, okay, where now this is an interesting picture. I tend to use it. I normally show it very early in the presentation, but because I've annotated it, it comes in useful later. All right. So there are 5 panels here. Each panel is the same width here, but the time scale is different. All right. This panel is 400 years, but we see it goes to tens of thousands, hundreds of thousands, millions, and tens of millions. All right? So we had 2 million years of ice age cycles, 50 million years. If we were to assume that this, see, it looks like a fairly, what do you call it, symmetric curve, right? But when you consider, if I were to use this scale and have 5 of them here, we would have 2,000 years here. I would need 25,000 screens to go back to 50 million years. 25,000 screens, if I use that scale. If I use that scale here. Okay? In no way is this symmetrical. Any one of these frames anywhere here will be a straight line. Okay? That's how slow climate change naturally is. Okay? And we are doing this. Okay? 0.06 degrees per 100 years to 1.6, 0.06 to 1.6 and more per 100 years. Okay? So it's like jumping off a building with a parachute and jumping off a building without one. Okay? The speed is what will kill you. Because if you land slowly, you're not in trouble. If you land and you're moving fast, you're in trouble. Okay? So, I like to show this because, you know, Earth with 2 ice caps, this is the temperature regime. Earth with 1 ice cap, this is temperature regime. With no ice is that temperature regime. Because when we talk about all of these average global temperatures, it's all of these zones. Yes, it's only the first 10 kilometers of atmosphere, but it encompasses all of this. Right? And the places that change the most are here. at the equator, we don't change a whole lot. Right? So what does the previous slides with the vegetation and all tell us? That tells us that this actually should end somewhere here, and this should move there. So more recently, we were actually more ice-free than we thought. Right? And once again, like I said, this is data that was collected in the 50s and 60s. And then we didn't have the techniques to date it. And because they were kept so well, we were finally able to use the modern techniques to date that material and actually bring this information to light, which makes Greenland look more and more and more green, more and more recently. All right? And that alone is not the problem. But the problem is if that ice is not there, then that ice is somewhere else. It's water. And that's what we need to be concerned about, because if you look at the most populated cities that are most at risk of sea level rise, you will find that Bangkok is one of them. Okay, of course, there are a lot of others. All right? But even though we don't have a capital that's right at the water's edge, or a large metropolis that's right at the water's edge, we still have much of our coastal infrastructure, ports, power stations, etc., that we'll need to consider how to deal with those. Okay? So, to wind up, we do see that the research on attribution is showing us that it is driving extreme weather events. There's a very strong pattern of attribution for some kinds of events. If you're going to adapt, reactive adaptation is not the way to go, because it's something that will force you to keep moving your goalpost and having you do that. So you need transformative adaptation if you want to reduce loss and damage. It must be transformative. Non-climate related extreme weather events like volcanic eruptions can impact climate systems, all right, over the span of years. Slow onset events such as sea level rise, such as air temperatures and glacial retreats can cause sudden onset events. There's a link. And then finally, the policy space that we thought we had to deal with sea level rise, we might not really have had after all. Okay? So, sorry? Yeah, yeah. I'm not an alarmist, because it doesn't pay to be alarmed. I think we would all want to take very rational measures, very concrete measures in the face of all of this information that's coming out from the scientific community, and move decisively earlier rather than later. Okay, we shouldn't be waiting for the rest of the world, the developed countries, to throw their hands up in the air and run around in circles. No, this information is now available to everyone, and the wise among us would look at that and say, geez, I think we should do something. And start putting the funds together, start putting the intra-ASEAN adaptation fund together, or these kinds of things. Maybe take a levy on the carbon trading between ASEAN member states. Start putting these structures together that will serve as a buffer when the time comes that we need them. Okay, so I hope that this has been, if not instructive, at least interesting. I'm always very nervous because the science can be hard to digest and confusing and dry, but I hope that I've given you sufficient food for thought that you want. Take this out and talk about it. Take it up with your board, take it up with the agencies that regulate you, the governments, etc. I'm happy to take questions.
Yes, sir.
Yes, sir.
Thanks. It's good that you mentioned board. Because Oliver from OCB.
The mic is not on. Could
Is
you
it
check its mic?
on? I think.
Is it not?
Can hear from there. Hear better?
A little bit.
Okay. No, because you mentioned board, and that's basically the challenge that I think quite a few of us face. I know there's some heads of sustainability, some CSOs around the room, and that's the disconnect that it's not a disconnect. It's the challenge that we face on a daily basis, right? So these are the realities of corporate, and I think even within this room, we know we are sitting in a silo. You mentioned Greenland, you mentioned USGS. Is USGS even funded right now? I'm not sure. So that's the reality, right? And we have to face that reality and speak clearly with our boards, with our stakeholders. And the honest truth is, I've been in this space. I've followed you for years. We've been in this space. We've done this for the last 5 years. Cooler Earth has been around. NCGS has been running. Have we made a change? I don't know. I don't know. And the reason why I'm saying that is because when I still talk to boards, and I've been in a few corporates, there's still a disconnect. And they are generally older. They don't have a lot of time left on Earth. I don't know. I'm not saying anything negative. I'm just talking about the reality. And they're male. They're male. They're white haired, and that's how it is, right? So I've got no head. I'm also a bit of white hair already.
White to know, yeah.
But they can't absorb this information. That's number one. We've tried. I've tried. I'm sure you have engaged with boards too. I don't know how receptive they've been. So there's an 80-20 rule, right? I do think it's sufficient to have 80% of this knowledge at the board level. And then I was hoping today you'd talk about adaptation solutions, and that's where we're heading to, right? So from the financial perspective, we've been here on Sunday. We were here too on a consultation, and we were talking. And I do hear and I do interact with the nature experts who are asking for the financing, but I didn't say anything then. But I'll share it with you. All banks and the financial sector has a fiduciary duty to investors, to holders of capital. You and I have retirement funds. So every single ringgit that we allocate to solutions needs to be feasible, right? So we can't be, there's altruistic funds, fine, but there's also very important investment returns. And what we talked about yesterday at the panel was to have backstops and guarantees for adaptation financing. So I do think, I hope, and yeah, I don't know, this is maybe not a question, it's more of a rant and a comment. If you can, well, first of all, the people in this room are good. I mean, we're all interested, but obviously the audience should be more at the board level. I hope they spend the effort, to understand these things, but also to provide very clear structures that can support adaptation and absorb. I mean, the financing is available. We talked about this. The money is there. The capital is there. But how do we justify putting in the money to and part of this is public responsibility, as in government responsibility, and how much can the private sector do our part? Yeah.
No. Okay. So yes, FIDE Forum. Okay. ICDM. We're trying to get this information out to them as quickly as possible, so they also understand this. My rant is that I can't get them in a room and talk to them face to face. They always want to be virtual. And I know, okay, that even as I'm talking, they are scrolling because they have fiduciary responsibilities, and they're chasing that. So I have one ear on it. I mean, I wish they could all be like Datuk Faiz yesterday. Was it yesterday or day before yesterday? Day before yesterday. Yeah, completely on the ground, in touch, understanding and moving. And I was very glad when he got in as chair, because I was hoping that he could drive some of this from that position as well. But yes, I do take the message that maybe we should have new, younger and more. Yeah, no, that's always the problem with the science, because the science has to then filter out and become policy. Policy has to become action plans, budgets, annual development plans, etc., etc. But what I'm trying to say is that we need your help to go to I mean, as a policymaker, civil servant for my career, I banged my head against the wall, and oftentimes it was against the private sector as well, because all I heard back all the time was, what's the incentives, what's the, but now being on the side of the fence that I am on and speaking directly to boards and chairs, etc., okay, I do get a sense now that, with global regulatory structures in place, and despite all the pushback, okay, on balance, with the information that's coming from the scientific community, there is reason enough to encourage boards to begin moving seriously on some of these things. It's not an answer to your question, but I can't train everyone all the time at all times. And yes, Daryl, go ahead. Okay, all right.
So, in response to this gentleman, as you know, Gary, I sit on some boards. I advise boards. I'm not a board member. I advise boards. And I also recognize that among the youth these days, I mean, the younger generation, there's this term called eco-depression, right? The feeling of
eco-anxiety.
You can't do anything lah. So might as well lie down and die lah, right? Elon Musk takes it to another level. He's quite certain that Earth is doomed. That's why he's going to Mars, and he's going to populate Mars himself. So, if I were to give advice to the younger one, number one, we have no option lah, so we have to be positive lah, right? So number one. Number two, facts never make people act. I don't know if you know this. You think it does, but it doesn't.
True.
Emotions always wins. If you combine emotion plus facts to back up those emotions, you'll probably get action. 3, in my work with corporates everywhere, sometimes they need a crisis before they act. So I always tell my teams before, never waste a crisis. Have something in your pocket just waiting for that crisis to happen, and then you give it all out. That same day the crisis happened, that's the time you come up with a solution. Never waste the crisis. I always find that very useful. 3, the people from internally, unfortunately, they always say, right, the prophet is always the guy that comes with his suitcase, right? Because they never believe people internally. That's how I make my living. I'm always the prophet with the suitcase. I'm the external guy. So have an external guy somehow, or find someone that they believe and trust. Boards don't believe, they won't swallow, even though if it's factual and emotional, if it's coming from someone they don't trust, they don't know, it won't happen. So those are just my words of some advice, and to give some hope to those, because I'm usually quite bleak. As Gary will know, I start my presentations all very bleak. And mostly why I start my presentations bleak is because a lot of people don't know that they don't understand a whole lot of things, right? And you can't get to the solutions if you don't ask the right questions. And you can't ask the right questions if you don't believe you have any blind spots. Thank you.
Yes, please. So, thank you very much, Daryl. For those of you who don't, Dr. Darrell used to head RSPO for many years before he retired, but still advises boards very actively. Yes, please go ahead.
Hi, I'm Shireen. I'm from Faculty of Medicine, UNC Malaya. I'm also head of sustainability, Faculty of Medicine and UNC Malaya Medical Center, MMC. So I'm a surgeon and an educator. And I just wanted to speak to jaded gentleman over here.
No, I can attest that he's not jaded.
This is a very recent foray of healthcare into sustainability. And I think a lot of times it's because we get a free pass. When I speak to my friends in finance, they say, oh, isn't healthcare sustainable? And I will educate them, no, healthcare is not sustainable. This has an impact on the environment. We form, I think, between 5 to 8% of global carbon footprint. That's more than aviation and shipping combined. And then oh, okay, so we need to do something about it, indeed. So where we are at Faculty of Medicine and UMMC is that we're actually now engaging our younger generation. So we're integrating climate change content into our medical curriculum. We're the first public university in the country to do so. And I think that's really where change needs to happen. Because you said, you know, old white men, no hair, maybe got hair. But our younger generation needs to understand the seriousness of this issue. The other thing is that apart from educator, I'm a surgeon. So I've been speaking to my surgical fraternity actually in the country, outside the country, and they're actually really, really receptive. So 2 weeks ago, I was speaking in Taiwan on sustainability and surgery. And that sparked a conversation which is going to lead to a joint advocacy statement in the ASEAN Federation of Surgical Colleges, which is amazing.
Yep.
I mean, I think that's really encouraging. It's fascinating for me as a healthcare worker to sit amongst finance people. I'm hearing and learning so many things which are very useful to me. I think that's the data I need to use. I think to echo Dr. Darrell, I always say actually facts are facts. Change comes from the heart. So we need to change heart. Thank you.
Thank you. Thank you very much. Any other questions? Yeah, oh yeah. Yeah. Sorry. I'll take it. Yep.
Hello, I'm Jun. I'm a carbon project developer, so you know I might be a bit biased here, but to me it seems that we have a carbon dioxide problem in air. And I think, you know, we should know that, you know, there are many ways to remove carbon dioxide from the air. And this region is blessed with a lot of biomass. So far, the most economical and technology-proven way to take carbon out from the air is to convert biomass into something called biochar, right? And this biochar is actually, you know, a regenerative substance that can go back to the fields to encourage more and more profitable biomass growth. Yeah, but you know, having worked on this for a year, I just sold 5 tons of biochar at 800 ringgit. But we need to be selling more, right? More people should be buying, you know, a couple of thousand tons, right? So that we can get this industry going. But I think, you know, as a young guy, there are many sectors in the economy that is hard to abate, right? The most direct way to do your part, right, is to look into a concept called CDRs, right, which are carbon dioxide removal credits. It's picking up a lot in the developed countries. So if anyone wants to know more about it, you know, come talk to me.
Okay, thank you. I think yeah, with the carbon capture, use and storage bill out there, you know, there's been more focus on removal and storage, and I've always been a outspoken proponent of biochar, because if you're going to inject CO2 into the ground, for every 1 carbon you inject, you're injecting 2 oxygen. It doesn't make sense to me. Your biochar is almost 100% carbon. Whatever you put it in, 75. Oh, you know, depends on the biochar, and depends on the feedstock and all that, and the process. But you know, we've got concrete trying desperately to be green. Okay, they mix fly ash in the concrete. If you mix biochar in the concrete instead of fly ash, if it has no, I think they've done the studies on the bearing strength, no change over time, even things like that. you could seriously remove it. And the beauty of biochar is its flexibility. You could use it as a fuel, it's a biofuel. You could use it, it's like biocoal, okay? You could use it as a commodity, make activated carbon, filter water, filter air, etc. You could, and then you could use it for carbon credits if the carbon price is good. Malaysia, we're always known for being very, very inflexible in our programs. We need to bring that flexibility in. Thank you very much. Any others before I'm running up on my time, but yeah, please go ahead. There's one question in the back. Can you help me pass it, Steve? Thanks, Steve.
Right. Hi. Probably not a question, but another rant.
Fine.
So just now you have a slide on the adaptation. So the transformative adaptation would be better than reactive adaptation. But the reality, probably not representing the company that I'm working now, but my previous companies. The issue is working with private companies. There's a situation whereby we have to do reactive adaptation because we need to rectify the issue immediately. For instance, like the utilities that you mentioned just now. And if we are to develop a transformative adaptation, that will take a number of stakeholders, including the regulators, which that would take a lot of time. So, like for instance, let's say this specific utility has to rectify a pipe, say, you know, like you just have to fix it, or else like the end user or the public will not be able to use that pipe. And the private company has to fork out the money to actually rectify that. But it doesn't solve the issue about, like you mentioned just now, the soil conditions and so on, which would have to involve the like majlis, you know, like other authorities, even the state government perhaps. So I think like in the bigger picture, as we move over time, we would always end up with reactive adaptation without being able to have time to actually implement the transformative adaptation. So I think it's, how do we manage that, you know, doing both at the same time?
Thank you for the question, and it's a very good question, but I think in my welcoming remarks also I already said that, you know, there is no time for this, and then as much as you say there may not be a budget for the kind of transformative, at least you should implement reactive in a way that it adds some transformative elements to it. You know, we can't do everything all at once, but we really do need to begin putting very strong foundations in new places immediately. You know, if I were still in government, I would be advising YB to advise his fellow ministers to already be looking for relocation land for all of the key infrastructure. You know, I would already be telling NARIM to do the modeling for, you know, 0.5 meter sea level rise, 1 meter sea level rise, and look at where the safe havens would be to begin planning relocation of key infrastructure to make sure that, you know, once again, and nothing wrong with living on floodplains. If you choose to live on a floodplain, you should be allowed to live on a floodplain. You should just not be allowed to get your house flooded out, you know, twice a year or 3 times a year, and then require assistance to, you know, no. So once again, like we did in the old days, you build your rumah tiang. and I mean, as a very young person, I lived in Kelantan, and some rumah tiang were very tall, you know, and I just came back, well, last year went to Brisbane, and they've adapted. Some rumah are now on tiang that are 4-5 meters tall. And now, of course, they're concrete tiang, no, steel tiang, no? not wooden tiang like we had. But it's adaptation that doesn't mess with the original function of the land, as it were. Okay, and it doesn't displace the water to somewhere else where it damages, somebody else or somebody else's stuff. So yeah, please.
A follow-up from what she said earlier.
Yeah.
One of the things that she actually mentioned is like you want to do some changes, you have to follow a lot of new laws, new regulations, regulators, and all that. A lot of red tapes. And we have seen, like, also going back to the question the gentleman said about board, why sometimes board are a bit, I wouldn't say the word reluctant, but they're a bit, not so welcoming in certain things. Now, sometimes we see that we are trying to solve one problem. When we talk about sustainability, we are trying to solve one problem. And we go back to the alphabet of ESG. We are trying to solve E. But then, to solve E, we have to do something which lead us to G. GE, when I'm talking about G, I'm talking about corruption. Now, this is reality, yeah? Reality, I have heard board talking about this as well. You want to solve one problem, but so much of red tapes. I want to do it fast. I have reporting, I have to do this. Now, for that, I have to expedite certain things, and I have to bridge certain things under the G. Now, we are not looking at the bigger picture, sustainability. We are solving one problem, but we are contributing to another problem.
Yep.
And this is widely happening. Huh?
Okay, sometimes my solution is Daryl's solution is, create a crisis. He says, don't waste a crisis. I say, if you need a crisis, you can create one. Create it. He's nodding. Yes. And I think create the crisis and shake everything up. Because, at the very least, it's going to come back down, even if it doesn't come, even if it doesn't settle out completely the way you want it to settle out. That shaking up might actually wake some people up that should be taking care of the G part or taking care of the S part, or
We already have Malaysian Transparency International. We have many C4. I can name it.
Yeah.
They're all shaking it, but does it make any impact? No.
No. I would respectfully disagree and say that no. For those who are listening, it is welcome. But once again, I will go back to what I also said yesterday and say that when you see something right and you are quiet about it, you are equally guilty. Even compared to if you see something wrong and you're quiet about it. Okay, so the affirmation for policymakers and decision makers is more important because it means that what they are already doing, they know they should continue, they will continue to do it. Whereas if you get on the case about things that they're not doing properly, they still are vacillating, they don't know what to do. All right? So yeah, this is meandering into an area that's a bit difficult to manage. Please. I'm holding you up from your lunch. I'm sorry.
Just wanted to clarify because what I said earlier, I don't really care about whether the board minds or not. Because the truth is, if you look at how, I'm just talking from the financial perspective, right? Money has gone into mitigation a lot. Solar is very well funded. So if you go and ask for a solar panel now, you got 5-10 banks willing to offer you financing. So why is that not happen on the adaptation side? My point really I wanted to get across was we just need more feasible solutioning on the adaptation side.
Okay.
That's all
Right. Point taken, and I agree with you. And once again, it has to be more transformative than reactive. It can be preventive, if you ask me. That's the best thing, preventive. Yeah. Yeah. Okay. thank you for your attention. You've been very, very kind to me. Given the fact that, it's a world of rants out there for those of us who've been in this for a while and, pulling our hair out every time we see things that are, not the way they should be. But it's only the first day of workshops and masterclasses. I wish you a very productive time in others that you might have signed up and registered for. Okay? Thank you very much. Oh, wait, we have I need to put this up. Yeah.
Okay.
Yeah.
Test.
So
Let's give a big round of applause.